Hello, everyone. My name is Svetlana Korneychuk. I'm from Karlsruhe Institute of Technology. And today I'm going to talk about insights into measuring local hydrogen concentration in palladium nanoparticles via in-situ gas TM. This talk is featuring our recent publication in Small about local hydrogen concentration and distribution in palladium nanoparticles and in-situ STEM EELS approach. So why palladium? Palladium is a very good model system to study hydrogen absorption and desorption in FCC metals. So in the temperature range which we are interested in, it has only two phases, a solid solution with very low hydrogen concentration and palladium hydride with a concentration more than 60% of atomic hydrogen in palladium. So what you're looking at here, this is pressure concentration isotherms for bulk palladium. Here you can see how hydrogen is getting absorbed in palladium at different temperatures. So, for instance, if we look at the isotherm for 20 degrees, at very low concentrations and pressures, concentration almost linearly grows with pressure. This is solid solution region. And then at this point, palladium hydride starts to form, and we're entering so-called two-phase field. So this white region is a two-phase field. We have two phases, solid solution and the hydride. And here the pressure, hydrogen pressure outside of the sample doesn't change because the hydride is forming, absorbing all the hydrogen. And here it keeps forming until the whole sample is hydrogenated, and then the pressure starts to grow again rapidly with the concentration. So what we did in our experiment, we kept the pressure constant about 13 kilopascal, and then we just changed the temperature. So from going at 160 degrees Celsius to 70 degrees Celsius, one can transfer from solid solution to hydride and observe the hydrogenation of the palladium nanoparticles. So yes, here we study not the bulk palladium, but palladium cubic nanoparticles. They are more interesting because here you can also study nano-sized effects. Well, in a nanoparticle, we have much higher surface to volume ratio and some elastic constraints, which I will talk later. So the goals of this research was actually try to measure the hydrogen concentration and to understand how the surface effects affect the hydrogen absorption in the nanoparticle. So we measured the concentration with EELS in TM when highly accelerated electrons of the primary beam interact with the sample. Some of them interact inelastically by losing part of their energy, exciting the electrons of the sample to the higher orbitals. You can measure this energy loss in the EELS spectrometer by separating the electrons in a magnetic prism and recording the EELS spectrum. It has been already shown in the articles of in article of Baldi and in range of articles by Jennifer Dion group that palladium bulk plasmon changes upon hydrogenation from about 7.8 eV to about 5.5 eV. They did this experiment in the environmental TM, and they were limited with the hydrogen pressure they could achieve, so they had to cool down the sample to actually observe the hydrogenation. Here we use the gas cell holder from Protochips. We are more flexible with temperature and pressure ranges, and we could create a situation where palladium hydride phase is stable, and we could do stimulus mapping of the palladium hydride and measure the concentration. So classically, in the bulk system, we have only well, two ranges of concentration: solid solution below 1% at room temperature and palladium hydride above 67% of hydrogen in the palladium. However, do we have some intermediate concentrations? Some theoretical papers said maybe, but it hasn't been shown so far. We found this theoretical article by Silkin, where they simulated the electric function of palladium-hydrogen systems for different concentration of hydrogen in palladium with time-dependent DFT simulations. So this graph shows you the imaginary part of the dielectric function for different hydrogen concentration in palladium. In principle, EELS spectrum should be identical to imaginary part of dielectric function if there is no retardation losses and if there is no inhomogeneity in the material itself. And we see that, well, this main peak, which corresponds to the bulk plasmon, it gradually, more or less gradually shifts to the lower energies with the increase of hydrogen concentration. But before showing the actual experimental results, we have to think how to properly evaluate them. Because in metallic particles, the plasmon signal at the surface is usually lower than in the middle. And we confirm this for palladium nanoparticles, both with simulations and with the experiment. We see that there is so-called red shift at the surface, and the plasmon signal is about 1 eV lower at the surface in a pure metallic nanoparticle than in the core. So that should be taken into account before evaluating the concentration of the particles. So I want to spend a bit more time again on this, explaining the simulations and how we evaluated the concentration of palladium hydrogen nanoparticles before actually showing you the experimental results, because this is important to understand how we calibrated the concentration. So we used again the simulations with MN-PBM toolbox. It uses boundary element method. There you just need to input your dielectric function of your material. For that, we used the simulated dielectric functions of palladium hydrogen system, extracted from the article which I showed you in one of the previous slides. And then you can create in this program whatever shape you need. And in principle, you can also create a substrate there. So we created this cubic palladium nanoparticle of 67 nanometers in diameter and measured how the EELS signal would look like in the core of the particle or at the edge or aloof. And we see that in this homogeneous particle with homogeneous hydrogen concentration, the tendency is similar to the bulk metallic particle. So basically, the signal at the surface is always lower than the signal in the core, even if the concentration is the same. So that should be taken into account when evaluating the experimental data. And the signal in the core could be, in principle, approximated with this linear equation. What we also simulated is a core shell situation. Because we have it in our experiment, we observe that the surface hydrogenates earlier and faster than the bulk. So here we have core shell. Core is a solid solution phase, and shell has different concentrations of hydrogen. And we see that the signal, EELS signal in the shell of the particle, again follows the same trend. It decreases with the increase of hydrogen concentration, and it's also very close to the surface signal in the case of this pure particle. So now I finally go to the experimental results. Just to be clear, so the whole experiment was acquired at 80 kilo-electron-volt, not only to get a better signal-to-noise ratio, but also to reduce Cherenkov radiation. That is quite important. At 300 kV, you will not get this data. The energy resolution I got with a monochromator was about 150 milli-electron volt already with silicon nitride membrane. So that was enough to evaluate the shift of the palladium hydrogen plasmon. As I said at the beginning, we kept the pressure constant in this experiment about 300 kilopascal, 13,000 kilopascal. And then we decreased the temperature from 160 to 60 degrees Celsius, observing the phase shift. So at the beginning, before the phase transition, the core of the particles, these are two particles marked by the dashed line, they remain in the solid solution phase. However, the surface of these particles starts to hydrogenate, forming some intermediate concentrations in between solid solution and the hydrate. When the phase transition happens, we still see that the concentration at the surface is higher than in the core of the particle, even taking into account this original shift of the surface plasmon, which I was talking about in the previous slide. And we also see that the hydrogen is unevenly distributed within the particle. When we start to dehydrogenate the sample by increasing the temperature, we see how the hydrogen leaves our particle from the core to the shell of the particle. We also see hysteresis, meaning that at the same temperature and pressure, during hydrogenation, the particles are in solid solution phase, and during dehydrogenation, they are in the hydrate phase. This is quite normal for palladium system. What is also interesting is that after the hydrogen left the core, the shell still remains in palladium hydride phase, at least within the scope of this experiment of about 10 minutes. If we look at the average concentration of hydrogen within this agglomeration of palladium nanoparticles, it corresponds actually to the bulk concentration for the solid solution phase for this kind of temperatures, for the high temperatures, and for the hydrate phase. However, distribution of hydrogen, you see the bars change, and each bar corresponds to a certain concentration. They change quite a bit with temperature, so hydrogen redistributes within the particle. So importantly, we showed that the concentration at the surface can be in the intermediate range, which confirms some previous literature suggestions. However, we also saw that hydrate can also form at the surface, which goes beyond what was suggested in the literature before. We also see similar behavior of the nanoparticles with slightly higher pressure. So the same experiment, just the pressure is twice as high as before. Particles start to hydrogenate at slightly higher temperatures, but we see all the same trends. Average concentration within the particles in solid solution phase and in hydrate phase is more or less the same. However, hydrogen is getting redistributed within the particle with the temperature change. Hydrogenation starts from the surface, and we also observe intermediate concentration at the surface. And I want to spend a bit more time talking about uneven distribution of hydrogen in the core of the particles, because it can be related to the pre-existing stresses in the nanoparticles. As discussed in the previous slides, the hydrogen distribution in the nanoparticles is uneven in some in the core of the nanoparticles. So the pre-existing strain could be the reason to that, and for that we estimated the strain in the nanoparticles without hydrogen and with the hydrogen with 4D stem with precession inside the atmosphere holder. So on the left, you can see the elastic strain maps for two nanoparticles. So this is one nanoparticle, this is the other one, without hydrogen. at 200 degrees centigrade, so it's quite high. There is no hydrogen in the nanoparticles. Then we decrease the temperature, particles hydrogenate, the lattice expands by about 3%. So we see this expansion with 40 stem, and then we heat them again. Hydrogen leaves the nanoparticles, and they go back to the initial strain state. And in this state, you see that there is a strong tensile strain of about 1.5% at the corners of the nanoparticles. What else do we see is that our nanoparticles hydrogenate at lower pressures at the same temperature than the bulk. This is shown by the Van Hoff's plot, which shows you the temperature and pressure of formation of palladium hydride in the bulk with the dotted lines. So it's hydrogen absorption and desorption, and with the dots, it is shown for our nanoparticles, and it's clearly visible that they start to hydrogenate at lower pressures at the same temperature, ranges. Pre-existing tensile strain at the corners of the nanoparticles could be the reason to that. In principle, chemical potential of hydrogen is determined by the hydrogen pressure outside of the nanoparticle, and it should be the same for the whole nanoparticle. So you see this. Yeah, it should be the same for the whole nanoparticle. This chemical potential is linked to the, for instance, hydrogen concentration CH, but also to the elastic stress in the system described by the stiffness tensor sigma. And the stiffness tensor could be linked to the elastic strain epsilon and epsilon 0. So epsilon is the initial strain in the nanoparticle, and epsilon 0 is the strain induced by hydrogen. But before particles start to hydrogenate at the very beginning, epsilon 0 is equal to 0, and epsilon is above 0 because it is tensile strain. So at the corners of the nanoparticles, the lattice is dilated. So this leads to the fact that the sigma tensor is above 0 at the start of the hydrogenation. Considering that the chemical potential within the nanoparticle should be the same everywhere, this leads to the fact that the concentration at the corners of the nanoparticle should be higher than in the middle of the nanoparticle at the beginning of the hydrogenation, which could explain the fact that we observe the hydrogenation at lower pressures than for the bulk. If you want to know more about strain vs hydrogen concentration relationship, you can check this article out. Okay, with that, I come with the conclusions of the talk. So with newly developed STEM EELS approach, we showed that we measure hydrogen concentration in palladium nanoparticles with a lateral resolution down to 4 nanometers. This resolution is determined by the delocalization of low-loss EELS signal. This technique is quite powerful. We show that at the beginning, hydrogen concentration increases in the near surface regions to the intermediate values between solid solution and the hydrate. And then it could already form a hydrate at the surface of the nanoparticles. We also showed that site and possible strain effects cause local variations in the hydrogen concentration and distribution in the nanoparticles, in particular in the hydrate phase. We also showed that the concentration of hydrogen can go up to 75% at the surface of the nanoparticles when they're completely hydrogenated. And this goes beyond the previous theoretical predictions. So if you want to repeat this experiment, I strongly encourage you to check the supplementary information of the article which I mentioned at the beginning, or you can directly contact me. I will be happy to help you. With that, thank you for your attention.